Hi. Yeah.
Is there any credit limit that we get from $500 credit that we got from Amazon? I did not put my name into any Excel sheet. I don't remember putting anything.
Oh, yeah. If you didn't put it in, then we didn't get one for you.
So then what we get?
Um,
I'm like so scared of using because they charge so much money. So
Yeah.
I'm just shutting it down like more
Yeah.
than using it.
Yeah. A few people missed putting their names in the spreadsheet, so I've asked if we can get some more.
So where should I put it?
Well,
Whom
it's
should I
it-
do
it's
that?
it's kind of too late now, so I'm going to have to wait until it comes up, and then we'll send you another message. So please keep a really close eye out for messages and follow all the instructions from us. Yeah.
You may want to take a look and see who your teammates are. If it's their seats close to you, you know, administration, you can start forming teams and start getting to know them and what to. Wait, no, there's none, sir.
We can just count.
Let me try and find out how numbers. Okay, numbers are on there.
Hi.
Hi. I can't seem to access the class wiki and stuff.
Okay. Have you given us your forum username?
I put it on the Excel sheet, but it was after that deadline.
Okay, did you check just now? Because I updated
you
it
just-
like a day ago or this
Oh,
morning.
I couldn't as of last night.
Try
I'll
again,
check
otherwise check with your
Yeah.
net. Okay.
It's that kind of day. Well, I have a cookie for you. Kind of keep me going. Yeah. To watch your just how that person was like.
Test.
It's like, "I want some cookie." And I was like, oh, we can start early. I got no response.
So there's a lesson through wiki post on the forum, and on that, in particular, there's something showing you how to update your Cressel repo or make sure your Cressel repo is installed. So just check that out if your Cressel notebook is not up to date or not working or anything like that. And your net, and your net's here if you need help. Okay, hi everybody.
Welcome. So I think hopefully all of our technology issues from last week are now fixed. It turns out that the Cresol issue is that it runs on top of AWS, and there was basically a limit had been placed on by AWS on the thing that Cresol was using. So that's now been lifted up to 600 instances, which should be enough for everybody here. And then the forum, I've upgraded it to a box that's 4 times bigger, and we've updated the software on it, so hopefully that should all be fine as well. So fingers crossed. Notice there's a lesson 2 wiki post on the forum that tells you how to make sure your Cresol is up to date. The slight complexity is that about a week ago, Cresol was updated so that the new FastAI repo was added to every new account. But a lot of you obviously were in the workshop at that point. It wasn't in every new account. So that's why there's 2 different parts. If you've got a more recent account, it'll already be sitting there in in courses/FastAI2. If you don't, then you would have to have Git cloned it yourself. So that's why it could be in one of 2 different spots. So the wiki hopefully explains that clearly. So we're going to do, I think we'll do the groups after break, because they forgot to put the group numbers out. So hopefully we'll deal with that during the break. Actually, Yanette, could you let them know at the registration that that's what we'll do? So we'll get them to come in at break and put all the numbers out there. Thank you. Great. All right, we're streaming, we're recording. Okay, so welcome back to Deep Learning Lesson 2. Last week we got to the point where we had successfully trained a pretty accurate image classifier. And so just to remind you about how we did that, can you guys see okay, I think? Actually, we can't turn the front lights off any better. So, all right. Can you guys all see the screen? Okay. We can turn just these ones, can we? Don't pitch us all into darkness, but if that works, then is that okay? That's better, isn't it? Yeah. Do you mind doing the other two, and maybe that one as well? No, not that one. Oh, that's great. Sorry, no, you're right. Just that one. Okay, great. That's better, isn't it? Cool. So just to remind you, the way that we built this image classifier was we used a small amount of code, basically 3 lines of code, and these 3 lines of code pointed at a particular path which already had some data in it. And so the key thing for this to know how to train this model was that this path, which was data, dogs, cats, had to have a particular structure, which is that it had a train folder and a valid folder, and in each of those train and valid folders there was a cats folder and a dogs folder, and each of the cats and the dogs folders was a bunch of images of cats and dogs. So this is like a pretty standard, it's one of 2 main structures that are used to say here is the data that I want you to train an image model from. So I know some of you during the week went away and tried different data sets where you had folders with different sets of images in and created your own image classifiers. And generally that seemed to be working pretty well from what I could see on the forums. So to make it clear, at this point this is everything you need to get started. So if you create your own folders with different sets of images, you know, a few hundred or a few thousand in each folder, and run the same 3 lines of code, that'll give you an image classifier, and you'll be able to see this 3rd column tells you how accurate it is. So we looked at some kind of simple visualizations to see like what was it uncertain about, what was it wrong about, and so forth, and that's always a really good idea. And then we learned about the one key number you have to pick. So this number here is the one key number, this 0.01, and this is called the learning rate. And so I wanted to go over this again, and we'll learn about the theory behind what this is during the rest of the course in quite a lot of detail. But for now, I just wanted to talk about the practice. Yes, Yanette, let me give you this.
So they cannot see you in the video. I guess
They can now. I just turned it around.
Oh, okay, perfect. I also was wondering, could you tell us about the other 3 numbers in that widget that you have right there?
These 3 here?
Yeah.
We're going to talk about the other ones shortly. So the main one we're going to look at for now is the last column, which is the accuracy. The first column, as you can see, is the epoch number. So this tells us how many times has it been through the entire data set trying to learn a better classifier. And then the next 2 columns is what's called the loss, which we'll be learning about either later today or next week. The first one is the loss on the training set, These are the images that we're looking at in order to try to make a better classifier. And the second is the loss on the validation set. These are the images that we're not looking at when we're training, but we're just setting them aside to see how accurate we are. And so we'll learn about the difference between loss and accuracy later. Okay, so so we've got the epoch number, the training loss is the second column, the validation loss is the third column, and the accuracy is the fourth column. Okay, so the basic idea of the learning rate So the basic idea of the learning rate is it's the thing that's going to decide how quickly do we kind of hone in on the solution. And so I find that a good way to think about this is to think about like, well, what if we were trying to fit to a function that looks something like this, right? We're trying to say, okay, whereabouts is the minimum point? This is basically what we do when we do deep learning, is we try to find the minimum point of a function. Now our function happens to have millions or hundreds of millions of parameters, but it works the same basic way. And so when we look at it, you know, we can immediately see that the lowest point is here. But how would you do that if you were a computer algorithm? And what we do is we start out at some point at random. So we pick, say, here, and we have a look and we say, okay, what's the loss or the error at this point? And we say, what's the gradient? In other words, which way is up and which way is down? And it tells us that down is going to be in that direction. And it also tells us how fast is it going down, which is, at this point, it's going down pretty quickly. And so then we take a step in the direction that's down. And the distance we travel is going to be proportional to the gradient. It's going to be proportional to how steep it is. The idea is, if it's steeper, then we're probably further away. That's the general idea, right? And so specifically what we do is we take the gradient, which is how steep is it at this point, and we multiply it by some number. And that number is called the learning rate, okay? So if we pick a number that is very small, then we're guaranteed that we're going to go a little bit closer and a little bit closer and a little bit closer each time, right? But it's going to take us a very long time to eventually get to the bottom. If we pick a number that's very big, we could actually step too far. We could go in the right direction, but we could step all the way over to here, right? As a result of which we end up further away than we started, and we could oscillate, and it gets worse and worse. So if you start training a neural net and you find that your accuracy or your loss is like spitting off into infinity, almost certainly your learning rate's too high. So in a sense, learning rate too low is a better problem to have, because you're going to have to wait a long time. But wouldn't it be nice if there was a way to figure out, like, what's the best learning rate? Something where you could kind of quickly go like, boom, 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 right? And so that's why we use this thing called a learning rate finder. And what the learning rate finder does is it tries, each time it looks at another, remember the term mini batch? A mini batch is a few images that we look at each time, so that we're using the parallel processing power of the GPU effectively. We look generally at around 64 or 128 images at a time. For each mini batch, which is labeled here as an iteration, we gradually increase the learning rate. In fact, multiplicatively increase the learning rate. We start at really, really tiny learning rates to make sure that we don't start at something too high, and we gradually increase it. And so the idea is that eventually the learning rate will be so big that the loss will start getting worse. And so what we're going to do then is we're going to look at the plot of learning rate against loss, right? So when the learning rate's tiny, it increases slowly, then it starts to increase a bit faster, and then eventually it starts not increasing as quickly, and in fact it starts getting worse. Right? So clearly here, and make sure you want to be familiar with this scientific notation. Okay, so 10 to the negative 1 is 0.1, 10 to the 0 is 1, 10 to the negative 2 is 0.01. And when we write this in Python, we'll generally write it like this. Rather than writing 10 to the negative 1 or 10 to the negative 2, we'll just write 1e neg 1 or 1e neg 2. Okay, they mean the same thing. You're going to see that all the time. So, and remember that equals 0.1, 0.01. Right. So don't be confused by this text that it prints out here. This loss here is the final loss at the end, and it's not of any interest, right? So ignore this. This is only interesting when we're doing regular training. It's not interesting for the learning rate finder. The thing that's interesting for the learning rate finder is this learn.shed.plot, and specifically, we're not looking for the point where it's the lowest, right? Because the point where it's the lowest, it's actually not getting better anymore. So that's too high a learning rate. So I generally look to see like where is it the lowest, and then I go back like 1 order of magnitude. So 1e neg 2 would be a pretty good choice here. Okay, so that's why you saw when we ran our fit here, we picked 0.01, right, which is 1e neg 2. So an important point to make here is like this is the one key number that we've learnt to adjust. And if you just adjust this number and nothing else, most of the time you're going to be able to get pretty good results. And this is like a very different message to what you would hear or see in any textbook or any video or any course, because up until now, there's been like dozens and dozens of these, they're called hyperparameters, dozens and dozens of hyperparameters to set, and they've been thought of as highly sensitive and difficult to set. So inside the FastAI library, we kind of do all that stuff for you as much as we can. And during the course, we're going to learn that there are some more we can tweak to get slightly better results. But it's kind of like, it's kind of in a funny situation here, because for those of you that haven't done any deep learning before, it's kind of like, oh, that's all there is to it. This is very easy. And then when you talk to people outside this class, they'll be like, deep learning is so difficult. There's so much to set. It's a real art form. And so that's why there's this difference, right? And so the truth is that the learning rate really is the key thing to set. And this ability to use this trick to figure out how to set it, although the paper is now probably 18 months old, almost nobody knows about this paper. It was from a guy who's not from a famous research lab, so most people kind of ignored it. And in fact, even this particular technique was one subpart of a paper that was about something else. So again, this idea of like, this is how you can set the learning rate, really nobody outside this classroom just about knows about it. Obviously, the guy who wrote it, Leslie Smith, knows about it. So it's a good thing to tell your colleagues about. It's like, here is actually a great way to set the learning rate. And there's even been papers called, like one of the famous papers is called No More Pesky Learning Rates, which actually is a less effective technique than this one. But this idea that like setting learning rates is very difficult and fiddly has been true for most of the kind of deep learning history. So here's the trick, right? Go look at this plot, find kind of the lowest, to go back about a multiple of 10 and try that, right? And if that doesn't quite work, you can always try, you know, going back another multiple of 10. But this has always worked for me so far.
Why does this learning rate, this method work versus something else like momentum based, or what's like the advantages and disadvantages with this learning rate like technique versus something else?
That's a great question. So we're going to learn during this course about a number of ways of improving gradient descent, like you mentioned momentum and atom and so forth. This is orthogonal, in fact. So one of the things the FastAI library tries to do is figure out the right gradient descent version. And in fact, behind the scenes, this is actually using something called atom. And so this technique is telling us this is the best learning rate to use, given what other tweaks you're using, in this case, the atom optimizer. So it's not that there's some compromise between this and some other approaches. This sits on top of those approaches, and you still have to set the learning rate when you use those other approaches. So we're trying to find the best kind of optimize it to use for a problem, but you still have to set the learning rate, and this is how we can do it. And in fact, this idea of using this technique on top of more advanced optimizers like Adam, I haven't even seen mentioned in a paper before, so I think this is like I mean, it's not a huge breakthrough, it seems obvious, but nobody else seems to have tried it. So as you can see, it works well.
When we use optimizers like Adam, which have like adaptive learning rates, so when we set this learning rate, is it like initial learning rate because it changes during the epoch, right?
So we're going to be learning about things like Adam, the details about it later in the class, but the basic answer is no. Even with Adam, there actually is a learning rate. It's just it's being basically divided by the gradient, the average previous gradient, and also the recent sum of squareds of gradients. So there's still like a number called the learning rate. There isn't even these so-called dynamic learning rate methods still have a learning rate. Okay, so the most important thing that you can do to make your model better is to give it more data. So the challenge that happens is that these models have hundreds of millions of parameters, and if you train them for a while, they start to do what's called overfitting. And so overfitting means that they're going to start to see like the specific details of the images you're giving them rather than the more general learning that can transfer across to the validation set. So the best thing we can do to avoid overfitting is to find more data. Now, obviously, one way to do that would just be to collect more data from wherever you're getting it from or label more data. But a really easy way that we should always do is to use something called data augmentation. So data augmentation is one of these things that's, in many courses, it's not even mentioned at all, or if it is, it's kind of like an advanced topic right at the end, but actually it's like the most important thing that you can do to make a better model. Okay, and so it's built into the FastAI library to make it very easy to do. And so we're going to look at the details of the code shortly, but the basic idea is that in our initial code, we had a line that said image classifier data from paths, and we passed in the path to our data. And for transforms, we passed in basically the size and the architecture. We'll look at this in more detail shortly. We just add one more parameter, which is what kind of data augmentation do you want to do? And so to understand data augmentation, it's maybe easiest to look at some pictures of data augmentation. So what I've done here, again, we'll look at the code in more detail later, but the basic idea is I've built a data class like multiple times. I'm going to do it 6 times, and each time I'm going to plot the same cat. And you can see that what happens is that this cat here is further over to the left, and this one here is further over to the right, and this one here is flipped horizontally, and so forth. So data augmentation, different types of image are going to want different types of data augmentation. Right? So, for example, if you were trying to recognize letters and digits, you wouldn't want to flip horizontally because like it actually has a different meaning. Whereas on the other hand, if you're looking at photos of cats and dogs, you probably don't want to flip vertically because cats aren't generally upside down, right? Whereas if you're looking at, there's a current Kaggle competition which is recognizing icebergs in satellite images, you probably do want to flip them upside down because it doesn't really matter which way around the iceberg or the satellite was, right? So one of the examples of the transform sets we have is transforms side on. So in other words, if you have photos that are like generally taken from the side, which generally means you want to be able to flip them horizontally but not vertically, this is going to give you all the transforms you need for that. So it'll flip them sideways, rotate them by small amounts, but not too much, slightly vary their contrast and brightness, and slightly zoom in and out a little bit and move them around a little bit. So each time it's a slightly different image.
I'm getting a couple of questions from people about, could you explain again the reason why you don't take the minimum of the loss curve,
Yeah.
but a slightly higher rate. So,
Yeah.
and also, could you, people want to understand if this works for every CNN, for CNNs, or for every neural net.
This
So
being the learning
a-
rate finder?
Yeah, exactly. Yeah. And should you call the students? We have a lot of.
Okay, great. Could you put your hand up if there's a spare seat next to you? Okay, so for the folks upstairs from MSAN, we have 9 spare seats, so come down and grab a seat. And if there is a spare seat next to you, when you see the MSAN folks coming in, please put your hand up to help them find it. And Jeanette, put that close to your mouth so they can hear you on the recording. So there was a question about the learning rate finder about why do we use the learning rate that's less than the lowest point. And so the reason why is to understand what's going on with this learning rate finder. So let's go back to our picture here of like how do we figure out what learning rate to use, right? And so what we're going to do is we're going to take steps, and each time we're going to double the learning rate, so kind of double the amount by which we're multiplying by the gradient. So in other words, we'd go tiny step, slightly bigger, slightly bigger, slightly bigger, slightly bigger, slightly bigger, slightly bigger. Okay? And so the question is, the purpose of this is not to find the minimum. The purpose of this is to figure out what learning rate is allowing us to decrease quickly, right? So the point at which the loss was lowest here is actually there, right? But that learning rate actually looks like it's probably too high. It's going to just jump like probably backwards and forwards, okay? So instead what we do is we go back to the point where the learning rate's quickly giving us a quick increase in the loss. So here is the actual learning rate increasing every single time we look at a new mini batch, right? So mini batch or iteration versus learning rate. And then here is learning rate versus loss. So here's that point at the bottom where it was now already too high. Okay, and so here's the point where we go back a little bit and it's still increasing nice and quickly. We're going to learn about something called stochastic gradient descent with restarts shortly, where we're going to see, like, in a sense, you might want to go back to 1e neg 3, where it's actually even steeper still, and maybe you would actually find this will actually learn even quicker. You could try it, but we're going to see later why actually using a higher number is going to give us a better generalization. So for now, I'll just put that aside. Just a moment. I need to click on the video. Thank you. Just a moment.
Do you mean
just
higher
a moment.
Learning rate?
Okay, go on.
Do you mean higher learning rate when you say higher?
Do I mean higher learning rate when I say higher?
Yeah.
Yes.
Or is it the higher iteration or something else?
I mean higher learning rate. So as we increase the iterations in the learning rate finder, the learning rate is going up. This is iterations versus learning rate. Okay, so as we do that, as the learning rate increases, and we plot it here, the loss goes down until we get to the point where the learning rate is too high, and at that point the loss is now getting worse.
Because I asked the question because you were just indicating that, you know, even though the minimum was at 10 to the minus 1, you suggested we should choose 10 to the minus 2, but now you're saying that maybe we should go back the other way, higher, so...
I didn't mean to say that. I'm sorry if I said something backwards. I want to go back down to a lower learning rate. So possibly I said a higher when I meant higher index.
So that's lower. Oh, you should...
Lower learning rate.
Okay,
yes.
Thanks.
Yep. So put up your hand if you've got a spot next to you. Is there a question over there? Or is yeah.
In last class, you said that all the local minima are the same, and this graph also shows the same. Is that something that was observed, or is that a theory behind it?
That's not what this graph is showing. This graph is simply showing that there's a point where if we increase the learning rate more, then it stops getting better and it actually starts getting worse. The idea that all local minima are the same is a totally separate issue, and it's actually something we'll see a picture of shortly. So let's come back to that.
Jeremy, do we have to find the best learning rate every time we are going to run an epoch?
Every time we're
running an epoch.
An epoch.
So how many times should I run this like learning rate finder during my training?
That's a great question, Yunette. I certainly run it once when I start. Later on in this class, we're going to learn about unfreezing layers. And after I unfreeze layers, I sometimes run it again. If I do something to like change the thing I'm training or change the way I'm training it, you may want to run it again, basically. Or, you know, particularly if you've changed something about how you train, like unfreezing layers, which we're going to soon learn about, and you're finding now the training is unstable or too slow, you know, again, you can run it again. There's never any harm in running it. It doesn't take very long. That's a great question. Okay, so back to data augmentation. So if we add to our, when we run this little transforms from model function, we pass in augmentation transforms. We can pass in, the main two are transforms side on or transforms top down. Later on, we'll learn about creating your own custom transform lists as well. But for now, because we're taking pictures from the side of cats and dogs, we'll say transform side on. And now each time we look at an image, it's going to be zoomed in or out a little bit, moved around a little bit, rotated a little bit, possibly flipped. Okay, and so what this does is it's not exactly creating new data, but as far as the convolutional neural net is concerned, it's a different way of looking at this thing, and it actually therefore allows it to learn how to recognize cats or dogs from somewhat different angles, right? So when we do data augmentation, we're basically trying to say, based on our domain knowledge, here are different ways that we can mess with this image that we know still make it the same image, you know, and that we could expect that you might actually see that kind of image in the real world. So what we can do now is when we call this from paths function, which we'll learn more about shortly, we can now pass in this set of transforms which actually have these augmentations in. Now, so we're going to start from scratch here. We do a fit, and initially the augmentations actually don't do anything. And the reason initially they don't do anything is because we've got here something that says pre-compute equals true. And we're going to come back to this lots of times. But basically what this is doing is, do you remember this picture we saw where we learned each different layer has these activations that basically look for, you know, anything from the middle of flowers to eyeballs of birds or whatever, right? And so literally what happens is that the later layers of this convolutional neural network have these things called activations. And an activation, literally, it's a number. An activation is a number that says this feature, like eyeball of bird, is in this location with this level of confidence, with this probability, right? And so we're going to see a lot of this later. But what we can do is we can say, all right, well, in this, we've got a pre-trained network, remember? And a pre-trained network is one where it's already learned to recognize certain things. In this case, it's learned to recognize the 1.5 million images in the ImageNet dataset. And so what we could do is we could take the second last layer, so the one which is like got all of the information necessary to figure out what kind of thing a thing is, and we can save those activations. So basically saving things saying, you know, there's this level of eyeballness here, and this level of dog's faceness here, and this level of fluffy ear there, and so forth. And so we save for every image these activations, and we call them the pre-computed activations. And so the idea is now that when we want to create a new classifier which can basically take advantage of these pre-computed activations, we can just very quickly train, we'll learn all the details of this shortly, we can very quickly train a simple linear model based on those. And so that's what happens when we say pre-compute equals true. And that's why, you may have noticed this week, the first time that you run a model, a new model, it takes a minute or two. Whereas you saw when I ran it, it took like 5 or 10 seconds. It took you a minute or two, and that's because it had to pre-compute these activations. And it just has to do that once. If you're using like your own computer or AWS, it just has to do it once ever. If you're using Crestle, it actually has to do it once every single time you rerun Crestle, because Crestle uses just for these pre-computed activations, it uses a special little kind of scratch space that disappears each time you restart your Crestle instance. So other than the special case of Crestle, generally speaking, you just have to run it once ever for a data set. Okay? So the issue with that is that since we've pre-computed for each image, you know, how much does it have an ear here, and how much does it have a lizard's eyeball there, and so forth, that means that data augmentations don't work, right? In other words, even though we're trying to show it a different version of the cat each time, we've pre-computed the activations for a particular version of that cat. So in order to use data augmentation, we just have to go learn.precompute equals false, okay? And then we can run a few more epochs, right? And so you can see here that as we run more epochs, the accuracy isn't particularly getting better, right? That's the bad news. The good news is that you can see the train loss, right? So this is like a way of measuring the error of this model. Although that's getting better, the error is going down, the validation error isn't going down, but we're not overfitting. And overfitting would mean that the training loss is much lower than the validation loss. And we're going to talk about that a lot during this course. But the general idea here is if you're doing a much better job on the training set than you are on the validation set, that means your model's not generalizing. So we're not at that point, which is good, but we're not really improving. So we're going to have to figure out how to deal with that. Before we do, I want to show you one other cool trick. I've added here cycle length equals 1. And this is another really interesting idea. Here's the basic idea. Cycle length equals 1 enables a fairly recent discovery in deep learning called stochastic gradient descent with restarts. And the basic idea is this. As you get closer and closer, to the right spot, right? I'm getting closer and closer. I may want to start to decrease my learning rate, right? Because as I get closer, I'm kind of like, oh, I'm pretty close now, so let's slow down my steps to try to get exactly to the right spot, right? And so as we do more iterations, our learning rate perhaps should actually go down, right? Because as we go along, we're getting closer and closer to where we want to be, and we want to like get exactly to the right spot. Okay, so the idea of decreasing the learning rate as you train is called learning rate annealing. And it's very, very common, very, very popular. Everybody uses it basically all the time. The most common kind of learning rate annealing is really horrendously hacky. It's basically that researchers like pick a learning rate that seems to work for a while, and then when it stops learning well, they drop it down by about 10 times, and then they keep learning a bit more until it doesn't seem to be improving, and then they drop it down by another 10 times. And that's what most academic research papers and most people in industry do. Right? So this would be like stepwise annealing, very manual, very annoying. A better approach is simply to pick some kind of functional form like align. It turns out that a really good functional form is 1/2 of the cosine curve, right? And the reason why is that for a while, when you're not very close, you kind of have a really high learning rate, and then as you do get close, you kind of quickly drop down and do a few iterations with a really low learning rate. And so this is called cosine annealing. So to those of you who haven't done trigonometry for a while, cosine basically looks something like this, right? So we've picked one little half piece. Okay. So we're going to use cosine annealing. But here's the thing. When you're in a very high dimensional space, right? And here we're only able to show 3 dimensions, right? But in reality, we've got hundreds of millions of dimensions. We've got lots of different fairly flat points. They may not be actual local minima, but they're fairly flat points, all of which are pretty good, right? But they might differ in a really interesting way, which is that some of those flat points, let me show you. Let's imagine we've got a surface that looks something like this. Right? Now, imagine that we kind of, our random guess started here, and our initial, therefore, kind of learning rate annealing schedule got us down to here. Now, indeed, that's a pretty nice low error, right? But it probably doesn't generalize very well, which is to say, if we use a different data set where things are just kind of slightly different in one of these directions, suddenly it's a terrible solution, right? Whereas over here, it's basically equally good in terms of loss, right? But it rather suggests that if you have slightly different data sets that are slightly moved in different directions, it's still going to be good, right? So in other words, we would expect this solution here is probably going to generalize better than the spiky one. So here's what we do, is we've got like a bunch of different low bits, right? Then our standard learning rate annealing approach will sort of go downhill, 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 downhill to one spot, right? But what we could do instead is use a learning rate schedule that looks like this, which is to say we do a cosine annealing and then suddenly jump up again and do a cosine annealing and then jump up again. And so each time we jump up, it means that if we're in a spiky bit and then we suddenly increase the learning rate and it jumps now all the way over to here. And so then we kind of learning rate anneal down to here. And then we jump up again to a high learning rate. Oh, and it stays here, right? So in other words, each time we jump up the learning rate, it means that if it's in a nasty spiky part of the surface, it's going to hop out of the spiky part. And hopefully if we do that enough times, it'll eventually find a nice smooth bowl.
Could you get the same effect by running multiple iterations through with different randomized starting points so that eventually you explore all possible minimas and then you can compare them?
Yeah, so in fact, that's a great question. And before this approach, which is called stochastic gradient descent with restarts, was created, that's exactly what people used to do. They used to create these things called ensembles, where they would basically relearn a whole new model 10 times in the hope that one of them's like going to end up being better. And so the cool thing about this stochastic gradient descent with restarts is that the model, once we're in a reasonably good spot, each time we jump up the learning rate, it doesn't restart. It actually hangs out in this nice part of the space and then keeps getting better. So interestingly, it turns out that this approach where we do this a bunch of separate cosine annealing steps, we end up with a better result than if we just randomly tried a few different starting points. So it's a super neat trick, and it's a fairly recent development, but and again, almost nobody's heard of it. But I found like it's now like my superpower. Like using this along with the learning rate finder, like I can get better results than nearly anybody, like in a Kaggle competition, you know, in the first week or two. I can like jump in, spend an hour or two, and bang, I've got a fantastically good result. And so this is why I didn't pick the point where it's got the steepest slope. I actually tried to pick something kind of aggressively high. It's still getting down, but maybe like getting to the point where it's nearly too high. And that's because I want to make sure, because when we do this stochastic gradient descent with restarts, this 10 to the negative 2 represents the highest number that it uses. So it goes up to 10 to the negative 2 and then goes down, and then up to 10 to the negative 2 and then down. So if I use too low a learning rate, it's not going to jump to a different part of the function.
So I have a few questions, but the first one is, how many times do you change the learning rate in one epoch?
We don't change the learning rate how many times okay, so in terms of this part here where it's going down, we change the learning rate every single mini batch, right? And then the number of times we reset it is set by the cycle length parameter. And so 1 means reset it after every epoch. So if I had 2 there, it would reset it after every 2 epochs. And interestingly, this point that when we do the learning rate annealing, that we actually change it every single batch, it turns out to be really critical to making this work. And it's very different to what nearly everybody in industry and academia has done before.
And when you get a chance, could you explain precompute equals true? Because it's still very confusing.
Yeah, we're going to come back to that multiple times in this course. So the way this course is going to work is we're going to like do a really high level version of each thing, and then we're going to like come back to it in 2 or 3 lessons, and then come back to it at the end of the course. And each time we're going to see like more of the math, more of the code, and get a deeper view. Okay, and we can talk about it also on the forums during the week.
So our main goal is to generalize, and we don't want to get those like narrow optimas.
Yeah, that's a very good summary.
So with this method, are we keeping track of the minimas and averaging them, kind of ensembling them?
That's another level of sophistication, and indeed you can see there's something here called snapshot ensemble. So we're not doing it in the code right now, but yes, if you wanted to make this generalize even better, you can save the weights here and here and here, and then take the average of the predictions. But for now, we're just going to pick the last one.
Okay, thank you.
If you want to skip ahead, there's a parameter called cycle save name, which you can add as well as cycle len, and that will save a set of weights at the end of every learning rate cycle, and then you can ensemble them. Okay, so we've got a pretty decent model here, 99.3% accuracy, and we've gone through a few steps that have taken a minute or 2 to run, and so from time to time I tend to save my weights. So if you go learn.save and then pass in a file name, it's going to go ahead and save that for you. Later on, if you go learn.load, you'll be straight back to where you came from. Okay, so it's a good idea to do that from time to time. This is a good time to mention what happens when you do this. When you go learn.save, when you create pre-computed activations, another thing we'll learn about soon, when you create resized images, these are all creating various temporary files, okay? And so what happens is, if we go to data, and we go to dogs, cats, this is my data folder, and you'll see there's a folder here called TMP, or TMP, and so this is automatically created, and all of my pre-computed activations end up in here. I mention this because if things aren't, if you're getting weird errors, it might be because you've got some like pre-computed activations that like were only half completed, or are in some way incompatible with what you're doing. So you can always go ahead and just delete this TMP, this temporary directory, and see if that causes your error to go away. This is the FastAI equivalent of turning it off and then on again. You'll also see there's a directory called models, and that's where all of these, when you say .save with a model, that's where that's going to go. Actually, it reminds me, when the stochastic gradient descent with restarts paper came out, I saw a tweet that was somebody who was like, oh, to make your deep learning work better, turn it off and then on again. That's this equivalent too. Is there a question there?
So if I want to, say I want to retrain my model from scratch again, do I just delete everything in the temp folder?
If you want to, if you want to train your model from scratch, there's generally no reason to delete the pre-computed activations, because the pre-computed activations are without any training. That's what the pre-trained model created with the weights that you downloaded off the internet. The only reason that you want to delete the pre-computed activations if there was some error caused by like half creating them and crashing or something like that. As you change the size of your input, change different architectures and so forth, they all create different sets of activations with different file names, so generally you shouldn't have to worry about it. If you want to start training again from scratch, all you have to do is create a new learn object. So each time you go like conf learner.pretrained, that creates a new object with new sets of weights for you to train from. Okay, so before our break, we'll finish off by talking about fine-tuning and differential learning rates. And so far, everything we've done has not changed any of these pre-trained filters, right? So we've used a pre-trained model that already knows how to find, at the early stages, edges and gradients, and then corners and curves, and then repeating patterns, and bits of text, and eventually eyeballs, right? We have not retrained any of those activations, any of those features, or more specifically, any of those weights in the convolutional kernels. All we've done is we've learnt some new layers that we've added on top of these things. We've learned how to mix and match these pre-trained features. Now, obviously, it may turn out that your pictures have, different kinds of eyeballs or faces, or if you're using different kinds of images like satellite images, totally different kinds of features altogether, right? So if you're like training to recognize icebergs, you're probably going to go all the way back and learn, all the way back to kind of different combinations of these simple gradients and edges. In our case, as dogs versus cats, we're going to have some minor differences, but we still may find it's helpful to slightly tune some of these later layers as well. So to tell the learner that we now want to start actually changing the convolutional filters themselves, we simply say unfreeze. Okay, so a frozen layer is a layer which is not trained, which is not updated. Okay, so unfreezes all of the layers. Now, when you think about it, it's pretty obvious that layer 1, right, which is like a diagonal edge or a gradient, probably doesn't need to change by much, if at all, right? From the 1.5 million images on ImageNet, it probably already has figured out pretty well how to find like edges and gradients. It probably already knows also like which kind of corners to look for and how to find which kinds of curves and so forth. So in other words, these early layers probably need little, if any, learning. Whereas these later ones are much more likely to need more learning. And this is universally true, regardless of whether you're looking for satellite images of rainforests or icebergs, or whether you're looking for cats versus dogs, right? So what we do is we create an array of learning rates where we say, okay, these are the learning rates to use for our additional layers that we've added on top. These are the learning rates to use in the middle few layers, and these are the learning rates to use for the first few layers. So these are the ones for the layers that represent like very basic geometric features. These are the ones that are used to for the more complex, kind of sophisticated convolutional features. and these are the ones that are used for the features that we've added and learned from scratch, right? So we can create an array of learning rates, and then when we call .fit and pass in an array of learning rates, it's now going to use those different learning rates for different parts of the model. This is not something that we've like invented, but I'd also say it's so not that common that it doesn't even have a name as far as I know. So we're going to call it differential learning rates. If it actually has a name, or indeed if somebody's actually written a paper specifically talking about it, I don't know. There's a great researcher called Jason Yasinski who did write a paper about the kind of the idea that you might want different learning rates and showing why. But I don't think any other libraries support it, and yeah, I don't know of a name for it. Having said that though, this ability to like unfreeze and then use these differential learning rates, I've found is like the secret to taking a pretty good model and turning it into an awesome model.
So just to clarify, so you have three numbers there,
right?
Three hyperparameters. The first one is for the late models, the late layers. The
other way around.
Layers are there in your model?
So we've the short answer is many, right?
Okay.
And they're kind of in groups, and we're going to learn about the architecture. This is called a ResNet, or residual network, and it kind of has ResNet blocks. And so what we're doing is we're grouping the blocks into three groups. And so this one is actually, this first number is for the earliest layers.
The ones closer to the data, the picture.
Yeah, the ones closest to the pixels that represent like corners and edges and gradients.
But why do you, but I thought those layers are frozen at first.
They are, right. So we just said unfreeze.
Unfreeze. Oh, so you're unfreezing them because you have kind of partially trained all the late layers.
We've trained our added layers, yes.
And now you're retraining the whole set.
Exactly.
I see. So, and the learning rate is particularly small for the early layers.
That's right.
Because you just kind of want to fine tune it. You don't want to.
Yeah, we probably don't want to change them at all.
I see.
But you know, if it does need to, then it can.
Thanks.
No problem.
He has a question.
So using the differential learning rates, how is that different from like grid search?
There's no similarity to grid search. So grid search is where we're trying to find the best hyperparameter for something. So for example, you could kind of think of the learning rate finder as a really sophisticated grid search, which is like trying lots and lots of learning rates to find which one is best. But this has nothing to do with that. This is actually, for the entire training from now on, it's actually going to use a different learning rate for each layer.
So I was wondering, so if you have a pre-trained model, then you have to use the same input dimensions, right? Because I was thinking, okay, let's say you have this big, they use like big machines to train these things and you want to take advantage of it. How would you go about, you know, if you have like images that are like bigger than the ones that they used, or?
We're going to be talking about sizes later, but the short answer is that with this library and the modern architectures we're using, we can use any size we like.
So Jeremy, do we need, can we unfreeze just a specific layer?
We can. We're not doing it yet, but if you wanted to, you can type learn.freeze_2 and pass in a layer number. Much to my surprise, or at least initial my surprise, it turns out I almost never need to do that. I almost never find it helpful. And I think it's because we're using differential learning rates. The optimizer can kind of learn just as much as it needs to. So yeah, it's.
What about if you have little data, like
very little data?
Very little data.
Yeah, it still doesn't
so.
seem to help. The one place I have found it helpful is if I'm using like a really big memory intensive model and I'm like running out of GPU. Having the less layers you unfreeze, the less memory it takes and the less time it takes. So there's that kind of practical aspect.
Yeah. To make sure also I asked the question right, can I just like unfreeze a specific layer?
No, you can only unfreeze layers from layer N onwards. You could probably delve inside the library and unfreeze one layer, but I don't know why you would. Okay, so I'm really excited to be showing you guys this stuff because it's something we've been kind of researching all year, is figuring out how to train state-of-the-art models. And we've kind of found these like tiny number of tricks. And so once we do that, we now go learn.fit, right? And you can see, look at this, we get right up to like 99.5% accuracy, which is crazy. There's one other trick you might see here, that as well as using stochastic gradient descent with restarts, i.e. cycle length equals 1, we've done 3 cycles. So earlier on, I lied to you. I said this is the number of epochs. It's actually the number of cycles, right? So if you said cycle length equals 2, it would do 3 cycles of each of 2 epochs. So it would do 6 epochs. So here I've said do 3 cycles, yet somehow it's done 7 epochs. And the reason why is I've got one last trick to show you, which is cycle molt equals 2. And to tell you what that does, I'm simply going to show you the picture. If I go learn.shed.plot learning rate, there it is. Now you can see what cycle molt equals 2 is doing. Okay, it's doubling the length of the cycle after each cycle. And so in the paper that introduced this stochastic gradient descent with restarts, the researcher kind of said, hey, this is something that seems to sometimes work pretty well. And I've certainly found that often to be the case. So basically, intuitively speaking, if your cycle length is too short, right, then it kind of starts going down to find a good spot, and then it pops out. And it goes down to try and find a good spot and pops out. It never actually gets to find a good spot, right? So earlier on, you want it to do that because it's trying to find the bit that's like smoother. But then later on, you want it to do more exploring and then more exploring, right? So that's why this cycle molt equals 2 thing often seems to be a pretty good approach, right? So suddenly we're introducing more and more hyperparameters, having told you that there aren't that many. But the reason is that like you can really get away with just picking a good learning rate, but then adding these extra tweaks really helps get that extra level up without any effort, right? And so in practice, I find this kind of 3 cycles starting at 1, molt equals 2 works very, very often to get a pretty decent model. If it doesn't, then often I'll just do 3 cycles of length 2 with no molt. Like there's kind of like 2 things that seem to work a lot. There's not too much fiddling I find necessary. And as I say, even if you use this line every time, I'd be surprised if you didn't get a reasonable result. Is there a question here?
Why does smoother surfaces correlate to more generalized networks?
So it's kind of this this intuitive explanation I tried to just killed the whole thing. I tried to give back here, which is that if you've got something spiky, right, and so what this x-axis is showing is like how good is this at recognizing dogs versus cats as you change this particular parameter, right? And so to something to be generalizable, it means that we want it to work when we give it a slightly different data set. And so a slightly different data set may have a slightly different relationship between this parameter and how catty versus doggy it is. It may instead look a little bit like this. Right? So in other words, if we end up at this point, right, then it's not going to do a good job on this slightly different data set. Or else if we end up on this point, it's still going to do a good job on this data set. Okay, so that's what cycle molt equals do. Okay, so we've got one last thing before we're going to take a break, which is we're now going to take this model, which has 99.5% accuracy, and we're going to try and make it better still. And what we're going to do is we're not actually going to change the model at all, right? But instead, we're going to look back at the original visualization we did, where we looked at some of our incorrect pictures. Now, what I've done is I've printed out the whole of these incorrect pictures. But the key thing to realize is that particularly, in fact, when we do the validation set, all of our inputs to our model all the time have to be square, right? And the reason for that is, it's kind of a minor technical detail, but basically the GPU doesn't go very quickly if you have like different dimensions for different images, because it needs things to be consistent so that every part of the GPU can do the same thing. Right? And I think this is probably fixable, but now that's the state of the technology we have. So our validation set, when we actually say for this particular thing, is this a dog? What we actually do to make it square is we just pick out the square in the middle, right? So we would take off its two edges, and so we take the whole height and then as much of the middle as we can. And so you can see in this case, we wouldn't actually see this dog's head. Right? So I think the reason this was actually not correctly classified was because the validation set only got to see the body, and the body doesn't look particularly dog-like or cat-like. It's not at all sure what it is. So what we're going to do when we calculate the predictions for our validation set is we're going to use something called test time augmentation. And what this means is that every time we decide, is this a cat or a dog, not in the training, but after we've trained the model, is we're going to actually take 4 random data augmentations. And remember, the data augmentations move around and zoom in and out and flip. Okay, so we're going to take 4 of them at random, and we're going to take the original unaugmented center cropped image, and we're going to do a prediction for all of those. And then we're going to take the average of those predictions. So we're going to say, is this a cat? Is this a cat? Is this a cat? Is this a cat? Right? And so hopefully, in one of those random ones, we actually make sure that the face is there, it's zoomed in by a similar amount to other dogs' faces it's seen, it's rotated by the amount that it expects to see it, and so forth. And so to do that, all we have to do is just call TTA. TTA stands for test time augmentation. This term of like, what do we call it when we're making predictions from a model we've trained? Sometimes it's called inference time, sometimes it's called test time. Everybody seems to have a different name. So TTA. And so when we do that, we go learn.tta, check the accuracy, and lo and behold, we're now at 99.65%, which is kind of crazy. Where's our green box? It was, oh, past there.
But for every epoch, we are only showing one type of augmentation of a particular image, right?
So when we are training back here, we're not doing any TTA, right? So TTA is not, like, you could, and sometimes like I've written libraries where after each epoch I run TTA to see how well it's going, but that's not what's happening here. I trained the whole thing with training time augmentation, which doesn't have a special name because that's what we mean. When we say data augmentation, we mean training time augmentation. So here, every time we showed it a picture, we were randomly changing it a little bit. So each epoch, each of these 7 epochs, it was seeing slightly different versions of the picture. Having done that, we now have a fully trained model. We then said, okay, let's look at the validation set. So TTA by default uses the validation set, and said, okay, what are your predictions of which ones are cats and which ones are dogs? And it did 4 predictions with different random augmentations, plus 1 on the unaugmented version, averaged them all together, and that's what we got, and that's what we calculate the accuracy from.
So is there a high probability of having a sample in TTA that was not shown during training?
Yeah, actually every data augmented image is unique because the rotation could be like 0.034 degrees and the zoom could be 1.0165. So every time it's slightly different.
Okay, thank you.
No problem. It's behind you.
What's your, why not use white padding or something like that? Just one of your...
White padding?
Like, just, you know, put like a white border around when you...
Oh, padding's not Yeah, so like there's lots of different types of data augmentation you can do, and so one of the things you can do is to add a border around it. Basically, adding a border around it in my experiments doesn't help. It doesn't make it any less cat-like. It's not, the convolutional neural network doesn't seem to find it very interesting, basically. Something that I do, we'll see later, is I do something called reflection padding, which is where I add some borders that are the outside just reflected. It's a way to kind of make some bigger images. Works well with satellite imagery in particular. But yeah, in general, I don't do a hell of a lot of padding. Instead, I do a bit of zooming.
It's kind of follow up to that last one, but rather than cropping, just add white space, because when you crop, you lose the dog's face. But if you had added white space, you wouldn't have.
Yeah, so that's where the kind of the reflection padding or the zooming or whatever can help. So there are ways in the FastAI library when you do custom transforms of making that happen. I find that it kind of depends on the image size, you know, but generally speaking, it seems that using TTA plus data augmentation, the best thing to do is to try to use as large an image as possible. And so if you kind of crop the thing down and put white borders on top and bottom, it's now quite a lot smaller. And so to make it as big as it was before, you now have to use more GPU. And if you're going to use all that more GPU, you could have zoomed in and used a bigger image. So in my playing around, that doesn't seem to be generally as successful. Okay.
There is a lot of interest on the topic of how to do data augmentation in other than images, in data that is not images.
Yeah. No one seems to know. I actually, I asked some of my friends in the natural language processing community about this, and we'll get to natural language processing in a couple of lessons. You know, it seems like it'd be really helpful. There's been a few examples, like a very, very few number of examples of people where papers would like try replacing synonyms, for instance, but on the whole, an understanding of like appropriate data augmentation for non-image domains is under-researched and underdeveloped.
The question was, couldn't we just use a sliding window to generate all the images? So in that dog picture, couldn't we generate 3 parts of that? Wouldn't that be better?
Yeah, for TTA, you mean?
Just in general, when you're creating your
So for training time, I would say no, that wouldn't be better, because we're not going to get as much variation. You know, we want to have it like 1 degree off, 5 degrees off, 10 pixels up, like lots of slightly different versions. And so if you just had 3 standard ways, then you're not giving it as many different ways of looking at the data. For test time augmentation, having fixed crop locations, I think probably would be better. And I just haven't gotten around to writing that yet. I have a version in an older library. I think having fixed crop locations plus random contrast, brightness, rotation changes might be better. The reason I haven't got around to it yet is because in my testing, it didn't seem to help in practice very much, and it made the code a lot more complicated. So, you know, it's an interesting question.
I just want to know, all these FastAI APIs that you are using, is it open source or it's
yeah, that's a great question.
ADAS?
So the FastAI library is open source, and let's talk about it a bit more generally, because you know, it's like the fact that we're using this library is kind of interesting and unusual, and it sits on top of something called PyTorch, right? So PyTorch is a fairly recent development, and it's kind of, I've noticed all the researchers that I respect pretty much are now using PyTorch. I found in part 2 of last year's course that a lot of the cutting edge stuff I wanted to teach, I couldn't do it in Keras and TensorFlow, which is what we used to teach with. And so I had to switch the course to PyTorch halfway through part 2. The problem was that PyTorch isn't very easy to use. You have to write your own training loop from scratch. You basically have to write everything from scratch. All the stuff you see inside the FastAI library, we would have had to have written it, you know, to learn. And so it really, makes it very hard to learn deep learning when you have to write hundreds of lines of code to do anything. So, so we decided to create a library on top of PyTorch because we, just our mission is to teach world-class deep learning. So we wanted to show you, like, here's how you can be the best in the world at doing X. And we found that a lot of the world-class stuff we needed to show really needed PyTorch, or at least with PyTorch it was far easier. But then PyTorch itself just wasn't suitable as a first thing to teach with for new deep learning practitioners. So we built this library on top of PyTorch, initially heavily influenced by Keras, which is what we taught last year. But then we realized we could actually make things much, much, much easier than Keras. So in Keras, if you look back at last year's course notes, you'll find that all of the code is 2 to 3 times longer. And there's lots more opportunities for mistakes because there's just a lot of things you have to get right. So we ended up kind of building this library in order to make it easier to get into deep learning, but also easier to get state-of-the-art results. And then over the last year, as we started developing on top of that, we started discovering that by using this library, it made us so much more productive that we actually started kind of developing new state-of-the-art results and new methods ourselves. And we started realizing that there's a whole bunch of like papers that have kind of been ignored or lost, which when you use them, it could like automate or semi-automate stuff like the learning rate finder that's not in any other library. So it kind of got to the point where now not only is kind of FastAI lets us do things easier, much easier than any other approach, but at the same time, it actually has a lot more kind of sophisticated stuff behind the scenes than anything else. So it's kind of an interesting mix. So we've released this library, like at this stage, it's like a very early version. And so through this course, by the end of this course, I hope as a group, we all a lot of people are already helping, have developed it into something that's, really pretty stable and rock solid. And yeah, anybody can use it to build your own models under an open source license. As you can see, it's available on GitHub. Behind the scenes, it's creating PyTorch models. And so PyTorch models can then be exported into various different formats. Having said that, like a lot of folks, like if you want to do something on a mobile phone, for example, you're probably going to need to use TensorFlow. And so later on in this course, we're going to show like how some of the things that we're doing in the FastAI library you can do in Keras and TensorFlow, so you can kind of get a sense of what the different libraries look like. Generally speaking, the simple stuff is like it'll take you a small number of days to learn to do it in Keras and TensorFlow versus FastAI and PyTorch. And the more complex stuff often just won't be possible. So like if you need it to be in TensorFlow, you'll just have to kind of simplify it often a little bit. But I think the more important thing to realize is every year the libraries that are available and which ones are the best totally changes. So like the main thing I hope that you get out of this course is an understanding of the concepts. Like here's how you find a learning rate, here's why differential learning rates are important, here's how you do learning rate annealing, here's what stochastic gradient descent with restarts does, so on and so forth. Because by the time we do this course again next year, the library situation is going to be different again. That's a question in the back.
I was wondering if you had an opinion on Pyro, which is Uber's new release.
I haven't looked at it, no. I'm very interested in probabilistic programming, and it's really cool that it's built on top of PyTorch. So one of the things we'll learn about in this course is we'll see that PyTorch is much more than just a deep learning library. It actually lets us write arbitrary GPU accelerated algorithms from scratch, which we're actually going to do. And Pyro is a great example of what people are now doing with PyTorch outside of the deep learning world. Great, okay, let's take a 8-minute break and we'll come back at 7:55. What are you giggling about?
Can I ask a question?
No! That was a question. Oh, great. We put them in groups of 6. No, that's going to be different teams for the rest of the class. So it's going to like 3, 3. Well, because we didn't actually get around to 3.
So for iceberg, I've been doing all like everything trying to like fine tune it.
Yeah.
Am I overplaying the top? I keep on like getting the.
Oh yeah. Oh, 7 is a 3.
So where should I stop and just like?
Well, I would just look where your validation starts getting better, right? So. Well, honestly, it's kind of all over the place. I think like you need to think about using maybe faster gradient as a restart, learning rate. Yeah, this is not looking good. Like you see how
try to fine tune it after.
no. If you can't fine tune it, see what's happening. Like this is zipping down, right? And this is not moving. So this just doesn't feel like you're in the right direction. No, because like I can have multiple ones. Oh. So you still like I haven't been well, parameters. No, the monostate dict contains parameters. Right. Well, no, the optimizer is just you pass in the parameters. So it's some subset. So like, yeah, so when you say optimize trees, then when it pulls out the parameters it requires for a subset of the parameters, that's the parameters that will be inside the optimizer. You can, yeah. Yes. Well, they're not the same. The subset that requires you to write it true. Then it's the same. Yeah. Then, so normally if you do a Python tutorial, it's not supposed to or it's passed through something like this before. No, the gradients do such variables. You can, once you put a variable, the dot gradient. Yeah, no, not no. Actually, I think something
because I wanted to just fall back in Python.
Always well, learn about input rates. Okay. Once you're kind of familiar with
So basically, like, I will do something every now Still, I mean,
So it's not gonna. Yeah, that's actually not Alright. Do you remember what time I said? Probably time, right? Okay, thanks everybody. Great. So just some of the questions I get at the breaks, I kind of say, could you ask on the forum or ask during class? And that's because, like, if you've got a question which isn't specific to you, it's very likely that other people would find it helpful as well. And so I feel like if I don't tell other people the answer and other people want to know the answer to that question, it's not fair to them, you know. So if I say that, please do ask, like put up your hand or ask on the forum, and that way I can give your answer more thought and, you know, do it in a way which helps not just you, but everybody. So, yes. Okay, where do the numbers run out? Okay, could you like maybe go through and just tell people like your team and just using incrementing numbers? Okay, so so I'm sorry about the trouble with Teams, but there's something that helped a lot in the last class, and I did want to get them up and running. So you've got a number in front of you. I'm sorry if last week you had a different number, but we didn't quite get them running. So this is actually your team. If you're an international fellow, your team is in the spreadsheet. So the way that this works is if you look at the forums, you can click on the little envelope, right? So you go up here and you click on the little envelope, and then there you can create a
you can create a new message, right? So one person in your team should create a new message to the other people in your team. So you can decide who that is. And once you've done that, you've now got like your own little private channel. Every time somebody types something there, it'll instantly update and you can use that to communicate. If you decide to use something else to communicate down the track, that's fine, but this is at least a starting point. And generally, we found people in past classes have found this a pretty effective way. Teams, it's up to you as to what you do, right? But what we often find is that the teams kind of help each other both during the course and after the course with the projects they're working on, you know, with anything that they can. Sometimes they get together with study groups and so forth. So what I want to do is take 5 minutes for you to turn to the other people in your team, or if you're an international fellow, in your private chat with your team. And 5 minutes is not long, right? So it's less than a minute each. Just say, what do you want to get out of deep learning? Right? What's the key thing that you're hoping to achieve? And also to make sure that you've shared your forum IDs so that you can continue the conversation afterwards. So let's take 5 minutes now to do that. If you don't have a team, put up your hand. Great. Okay, thanks everybody. Hope you've had a chance to say hi to your teammates. Let's continue. So, something else which, something else that past cohorts have found helpful is that is to get together during the week for a study group. If there are people talking around you, you can tap them on the shoulder and let them know. Okay, let's take a seat. So, one thing that previous cohorts have found helpful is that some folks that have been able to take some time during the week is that they've actually got together doing study groups and kind of talked to each other about deep learning, worked on projects together, or if there are concepts they want to dig into, they kind of work on that together. USF is available to you to do study groups, but it's kind of up to you to make that happen. So if you want to, you know, get together during the week in a study group, then probably best thing to do would be to send a private message to Yannet, or else to ask on the forum directly, and we can help you. We can show you how to get a room, and other people then you can say on the forum, I want to get together on Tuesday afternoon for a study group. We'll let you know if there's a room available, and you know, you can talk about whatever you want to talk about. So depending on my availability, I've often come to those study groups as well, and we've tended to do things like, oh, you know, here's an interesting Kaggle competition we want to work on together, or here's a, you know, let's go and actually have a look at that stochastic gradient descent with restarts paper and try reading it together, or, you know, different people have different interests. Or sometimes it's just like, gosh, I can't for the life of me get my Cressel instance running, you know, how do I fix this login problem or whatever. Okay. Another thing that's often happened is that people who maybe like live down in the South Bay, or if there are folks, international fellows who are in the same area, is to organize study groups in your area, wherever you happen to live. And again, you're welcome on the forum to post a thread saying, like, you know, South Bay thread here, and, you know, then anybody in the South Bay can post to that thread and say, oh, I live in the South Bay as well, so forth. The thread for the people here who are visiting from Australia would be a thread of 1, so that would be not so good, but you know. Okay, so 99.65% accuracy. What does that mean? So in classification, when we do classification in machine learning, a really simple way to look at the result of a classification is what's called the confusion matrix. This is not just deep learning, but in any kind of classifier in machine learning, where we say, okay, what was the actual truth? There were 1,000 cats and 1,000 dogs, and of the 1,000 actual cats, how many did we predict were cats? This is obviously in the validation sets. This is the images that we didn't use to train with. It turns out there were 998 cats that we actually predicted as cats, and 2 that we got wrong. Okay, and then for dogs, there were 995 that we predicted were dogs, and then 5 that we got wrong. And so often these confusion matrices can be helpful, particularly if you've got like 4 or 5 classes you're trying to predict to see like which group you're having the most trouble with. And you can see it uses color coding to tell you, to highlight the large bits. And you've got to hope that the diagonal is the highlighted section. So now that we've retrained the model, it can be quite helpful now that it's better to actually look back and see like, okay, which ones in particular were incorrect. And we can see here, there were actually only 2 incorrect cats. It prints out 4 by default, so you can actually see these 2 actually less than 0.5, so they weren't wrong. Okay, so it's actually only these 2 were wrong cats. This one isn't obviously a cat at all. This one is, but it looks like it's got a lot of weird artifacts and you can't see its eyeballs at all. So, and then here are the, how many dogs were there were wrong? There were 5 wrong dogs. Here are 4 of them. That's not obviously a dog. That looks like a mistake. That looks like a mistake. That one, I guess it doesn't really have enough information, but I guess it's a mistake. So, so we've done a pretty good job here of creating a good classifier. Based on entering a lot of Kaggle competitions and comparing results I've done to various research papers, I can tell you it's a state-of-the-art classifier. It's right up there with the best in the world. We're going to make it a little bit better in a moment, but here are the basic steps, right? So if you want to create a world-class image classifier, the steps that we just went through was that we turned data augmentation on by saying org transforms equals, and you either say side on or top down, depending on what you're doing. Start with precompute equals true, find a decent learning rate. We then train just like at 1 or 2 epochs, which like takes a few seconds because we've got precompute equals true. Then we turn off precompute, which allows us to use data augmentation to do another 2 or 3 epochs, generally with cycle length equals 1. Then I unfreeze all the layers. I then set the earlier layers to be like either somewhere between a 3 times to 10 times lower learning rate than the previous. So in this case, I did 10 times, right? So it's like this was my learning rate that I found from the learning rate finder, then I went 10 times smaller and then 10 times smaller. As a rule of thumb, like knowing that you're starting with a pre-trained ImageNet model, if you can see that the things that you're now trying to classify are pretty similar to the kinds of things in ImageNet, i.e. pictures of normal objects in normal environments, you probably want about a 10x difference because you want those earlier layers, like you think that the earlier layers are probably very good already. Whereas if you're doing something like satellite imagery or medical imaging, which is not at all like ImageNet, then you probably want to be training those earlier layers a lot more. So you might have like just a 3x difference. Right? So that's like one change that I make, is to try to make it either 10x or 3x. Yeah, so then after unfreezing, you can now call lrfind again, right? And I actually didn't in this case, but like once you've unfrozen all the layers, you've turned on differential learning rates, you can then call lrfind again, right? And so you can then check like, oh, does it still look like the same point I had last time is about right? Something to note is that if you call lrfind having set differential learning rates, the thing it's actually going to print out is the learning rate of the last layers, right? Because you've got 3 different learning rates, so it's actually showing you the last layer. So then, yeah, then I train the full network with cycle mult equals 2 until either it starts overfitting or I run out of time, right? So like, let me show you, right? So let's do this again for a totally different data set. So this morning, I noticed that some of you on the forums were playing around with this playground Kaggle competition, very similar, called dog breed identification. So the dog breed identification Kaggle challenge is one where you don't actually have to decide which ones are cats and which ones are dogs. They're all dogs, but you have to decide what kind of dog it is. And there are 120 different breeds of dogs. Okay, so, you know, obviously this could be like different types of cells in pathology slides. It could be different kinds of cancers in CT scans. It could be different kinds of icebergs and satellite images, whatever, right? As long as you've got some kind of labeled images. So I want to show you what I did this morning. So it took me about an hour, basically, to go end to end from something I'd never seen before. So I downloaded the data from Kaggle, and I'll show you how to do that shortly. But the short answer is there's something called Kaggle CLI, which is a GitHub project you can search for. And if you read the docs, you basically run kg download, provide the competition name, and it'll grab all the data for you to your Cressel or Amazon or whatever instance. I put it in my data folder, and I then went ls, and I saw that it's a little bit different to our previous data set. It's not that there's a train folder which has a separate folder for each kind of dog, but instead it turned out there was a CSV file. And the CSV file, I read it in with pandas. So pandas is the thing we use in Python to do structured data analysis, like CSV files. So if you pandas, we call PD. That's pretty much universal. PD.readCSV reads in a CSV file. We can then take a look at it, and you can see that basically it had like some kind of identifier, and then the breed, right? So this is like a different way. This is the second main way that people kind of give you image labels. One is to put different images into different folders. The second is generally to give you some kind of file, like a CSV file, to tell you, here's the image name and here's the label. Okay, so what I then did was I used pandas again to create a pivot table, which basically groups it up just to see how many of each breed there were, and I sorted them. And so I saw, okay, they've got like about 100 of some of the more common breeds, and some of the less common breeds, they've got like 60 or so. Okay, altogether there are 120 rows, so there must have been 120 different breeds represented. Okay, so I'm going to go through the steps, right? So enable data augmentation. So to enable data augmentation, when we call this transforms from model, you just pass in an aug transforms. In this case, I chose side on. Again, these are pictures of dogs and stuff, so they're side on photos. We'll talk about max zoom more detail later, but max zoom basically says when you do the data augmentation, we like zoom into it by up to 1.1 times. Okay, so but randomly between 1, the original image size, and 1.1 times. So it's not always cropping out the middle or an edge, but it could be cropping out a smaller part. Okay, so having done that, the key step now is that rather than going from paths, so previously we went from paths, and that tells it that the names of the folders are the names of the labels. We go from CSV, and we pass in the CSV file that contains the labels. So we're passing in the path that contains all of the data, the name of the folder that contains the training data, the CSV that contains the labels. We need to also tell it where the test set is if we want to submit to Kaggle later. We'll talk more about that next week. Now this time, the previous data set I had actually separated a validation set out into a separate folder, right? But in this case, you'll see that there is not a separate folder called validation, right? So we want to be able to track how good our performance is locally, so we're going to have to separate some of the images out to put it into a validation set. Okay, so I do that at random, and so up here you can see I've basically opened up the CSV file, turned it into a list of rows, and then taken the length of that -1, because there's a header at the top, right? And so that's the number of rows in the CSV file, which must be the number of images that we have. And then this is a FastAI thing, get cross-validation indexes. We'll talk about cross-validation later, but basically if you call this and pass in a number, it's going to return to you by default a random 20% of the rows to use as your validation set. And you can pass in parameters to get different amounts, right? So this is now going to grab 20% of the data and say, all right, this is the indexes, the numbers of the files which we're going to use as a validation set. Okay, so now that we've got that, in fact, let's kind of run this so you can see what that looks like. So val indexes is just a big bunch of numbers, okay, and so n is 10,000, right? And so we have about 20% of those is going to be in the validation set. So when we call from CSV, we can pass in a parameter which is to tell it which indexes to treat as a validation set, and so let's pass in those indexes. One thing that's a little bit tricky here is that the file names actually have, I checked, they actually have a .jpg on the end, and these obviously don't have a .jpg, so you can pass in, when you call from CSV, you can pass in a suffix that says that the labels don't actually contain the full file names. You need to add this to them, okay? So that's basically all I need to do to set up my data. As a lot of you have noticed during the week, inside that data object, you can actually get access to the data set by the training data set by saying train ds. And inside train ds is a whole bunch of things, including the file names. Okay, so train ds.filenames contains all of the file names of everything in the training set. And so here's like one file name. Okay, so here's an example of one file name. So I can now go ahead and open that file and take a look at it. All right, so that was the next thing I did, was to try and understand what my data set looks like, and it found an adorable puppy. So that was very nice. So feeling good about this. I also want to know, like, how big are these files, right? Like, how big are the images? Because that's a key issue. If they're huge, I'm going to have to think really carefully about how to deal with huge images. That's really challenging. If they're tiny, well, that's also challenging. Most of ImageNet models are trained on either 224 by 224 or 299 by 299 images. So anytime you have images in that kind of range, that's really hopeful. You're probably not going to have to do too much different. In this case, the first image I looked at was about the right size, so I'm thinking, oh, this is looking pretty hopeful. So what I did then is I created a dictionary comprehension. Now, if you don't know about list comprehensions and dictionary comprehensions in Python, go study them. They're the most useful thing, super handy. But you can see the basic idea here is that I'm going through all of the files, and I'm creating a dictionary that maps the name of the file to the size of that file. Again, this is a handy little Python feature which I'll let you learn about during the week if you don't know about it, which is zip, and using this special star notation is now going to take this dictionary and turn it into the rows and the columns. And so I can now turn those into NumPy arrays, and like, okay, here are the first 5 row sizes for each of my images. And then matplotlib is something you want to be very familiar with if you do any kind of data science or machine learning in Python. Matplotlib we always refer to as PLT, so it gives us a histogram, and so I got a histogram of how many rows there are in each image. So you can see here I'm kind of getting a sense. Before I start doing any modeling, I kind of need to know what I'm modeling with. And I can see some of the images are going to be like 2,500, 3,000 pixels high, but most of them seem to be around 500. So given that so few of them were bigger than 1,000, I use standard NumPy slicing to just grab those that are smaller than 1,000 and histogram that, just to zoom in a little bit. And I can see here, all right, it looks like, yeah, the vast majority are around 500. And so this actually also prints out the histogram, so I can actually go through and I can see, yeah, 4,500 of them are about 450. Okay, so I get about that sense of how many they are.
So, Jeremy, how many images should we get in the validation set? Is always at 20%?
So the size of the validation set, like, using 20% is fine unless you're kind of feeling like, oh, my data set's really small, I'm not sure that's enough. You know, like, if you've got Basically, think of it this way. If you train like the same model multiple times and you're getting very different validation set results and your validation set's kind of small, like smaller than 1,000 or so, then it's going to be quite hard to interpret how well you're doing. Now, this is particularly true like if you care about the third decimal place of accuracy, and you've got like 1,000 things in your validation set, then you're talking about like a single image changing class is changing, is what you're looking at. So it really depends on like how accurate how much difference you care about. I would say in general, like at the point where you care about the difference between like, I don't know, 0.01 and 0.02, like the second decimal place, you want that to represent like 10 or 20 rows. Like if you're changing the class of like 10 or 20 rows, then that's something you can be pretty confident of. So like most of the time, given the data sizes we normally have, 20% seems to work fine. But yeah, it's kind of it depends a lot on specifically what you're doing and what you care about. And it's not a deep learning specific question either, so for those who are interested in this kind of thing, we're going to look into it in a lot more detail in our machine learning course, which will also be available online. Okay, so I did the same thing for the columns just to make sure that these aren't like super wide, and I got similar results and checked in and again found they're kind of like 400 or 500, seem to be about the average size. So based on all of that, I kind of thought, okay, this looks like a pretty normal kind of image data set that I can probably use pretty normal kinds of models on. I was also particularly encouraged to see that when I looked at the dog, that the dog like takes up most of the frame, right? So I'm not too worried about like cropping problems, If the dog was just like a tiny little piece of one little corner, then I'd be thinking about doing different, maybe zooming in a lot more or something. Like in medical imaging, that happens a lot. Like often the tumor or the cell or whatever is like one tiny piece, and that's much more complex. So yeah, based on all that, this morning I kind of thought like, okay, this looks pretty standard. So I went ahead and created a little function called getData that basically had my normal 2 lines of code in it. But I made it so I could pass in a size and a batch size. The reason for this is that when I start working with a new data set, I want everything to go super fast. And so if I use small images, it's going to go super fast. So I actually started out with size equals 64, just to create some super small images that would just go like a second to run through and see how it went. Later on, I started using some big images and also some bigger architectures, at which point I started running out of GPU memory. So I started getting these errors saying CUDA out of memory error. When you get a CUDA out of memory error, the first thing you need to do is to go kernel restart. Once you get an out of memory error on your GPU, you can't really recover from it, right? It doesn't matter what you do, you have to go restart, okay? And once I restarted, I then just changed my batch size to something smaller. So when you create your data object, you can pass in a batch size parameter, okay? And like I normally use 64 until I hit something that says out of memory, and then I'll just halve it. And if I still get out of memory, I'll just halve it again, okay? So that's why I created this, to allow me to like start making my sizes bigger as I looked into it more, and as I started running out of memory, to decrease my batch size. So at this point, I went through this a couple of iterations, but I basically found everything was working fine. So once it was working fine, I set size to 224, and I created my pre-compute equals true. First time I did that, it took a minute to create the pre-computed activations, and then it ran through this in about 4 or 5 seconds, and you can see I was getting 83% accuracy. Now remember, accuracy means it's exactly right, and so it's predicting out of 120 categories. It's predicting exactly right. So when you see something with 2 classes is 80% accurate versus something with 120 classes is 80% accurate, they're very different levels, So when I saw like 83% accuracy with just a pre-computed classifier, no data augmentation, no unfreezing, anything else across 120 classes, I'm thinking, oh, this looks good, right? So then I just kind of kept going through our little standard process, right? So then I turn pre-compute off, okay? And cycle length equals 1, and I started doing a few more cycles, a few more epochs. So remember, an epoch is one pass through the data. A cycle is however many epochs you said is in a cycle. It's the learning rate going from the top that you asked for all the way down to 0. So since here cycle length equals 1, a cycle and an epoch are the same. Okay, so I did. I tried a few epochs. I did actually do the learning rate finder, and I found 1e-2 again looked fine. It often looks fine. And I found it kind of kept improving, so I tried 5 epochs, and I found my accuracy getting better. So then I saved that, and I tried something which we haven't looked at before, but it's kind of cool. If you train something on a smaller size, you can then actually call learn.setData and pass in a larger size data set. And that's going to take your model, however it's trained so far, and it's going to let you continue to train on larger images. And I'll tell you something amazing. This actually is another way you can get state-of-the-art results. And I've never seen this written in any paper or discussed anywhere. As far as I know, this is a new insight. Basically, I've got a pre-trained model, which in this case, I've trained a few epochs with a size of 224 by 224. And I'm now going to do a few more epochs with a size of 299 by 299. Now, I've got very little data, kind of by deep learning standards. I've only got 10,000 images, right? So with a 224 by 224, I kind of built these final layers to try to find things that worked well at 224 by 224. When I go to 299 by 299, I basically, if I overfit before, I'm definitely not going to overfit now. Like, I've changed the size of my images. They're kind of like totally different. But like conceptually, they're still the same kinds of pictures of the same kinds of things. So I found this trick of like starting training on small images for a few epochs and then switching to bigger images and continuing training is an amazingly effective way to avoid overfitting. And it's like, it's so easy and so obvious. I don't understand why it's never been written about before. Maybe it's in some paper somewhere and I haven't found it, but I haven't seen it.
Would it be possible to do the same thing using, let's say, Keras or TensorFlow as well, to feed an image of a different size?
Yeah, I think so. Like, as long as you use one of these more modern architectures, what we call fully convolutional architectures, which means not VGG. And you'll see we don't use VGG in this course because it doesn't have this property, but most of the architectures developed in the last couple of years can handle pretty much arbitrary sizes. Yeah, it'd be worth trying. Yeah, I think it ought to work. Okay, so I call getData again. Remember, getData is just the little function that I created back up here, right? GetData is just this little function, right? So I just passed a different size to it. And so I call freeze just to make sure that everything except the last layer is frozen. I mean, actually it already was at this point, so it didn't really do anything. You can see now with pre-compute off, I've now got data augmentation working, so I kind of run a few more epochs. And what I notice here is that the loss to my training set and the loss to my validation set loss is a lot lower than my training set. This is still just training the last layer. So what this is telling me is I'm underfitting, right? And so if I'm underfitting, it means this cycle length equals 1 is too short. It means it's like finding something better, popping out, and it's like never getting a chance to zoom in properly. So then I set cycle molt equals 2 to give it more time. So like the first time is 1 epoch, the second one is 2 epochs, the third one is 4 epochs, and you can see now the validation training are about the same. Okay, so that's kind of thinking, yeah, this is about the right track. And so then I tried using test type augmentation to see if that gets any better still. Didn't actually help a hell of a lot, just a tiny bit. And just kind of, at this point I'm thinking, okay, this is nearly done. So I just did one more cycle of 2 to see if it got any better, and it did get a little bit better again. And then I'm like, okay, that looks pretty good. I've got a validation set loss of 0.199. And so you'll notice here I actually haven't tried unfreezing. The reason why was when I tried unfreezing and training more, it didn't get any better. And so the reason for this clearly is that this data set is so similar to ImageNet that the training the convolutional layers actually doesn't help in the slightest. And actually, when I later looked into it, it turns out that this competition is actually using a subset of ImageNet. So that's why. Okay, so then if we check this out, 0.199 against the leaderboard. This is only a playground competition, so it's not like the best here, but you know, it's still interesting. It gets us somewhere around 10th or 11th. Okay, and in fact, we're competing against, I notice, this is a FastAI student, this is a FastAI student. These people up here, I know they actually posted that they cheated. They actually went and downloaded the original images and trained to that. So, and this is why this is a playground competition, they call it. It's not real, right? You know, it's just to allow us to try things out. But you can basically see out of 200 and something people, we're getting some very good results without doing anything remotely interesting or clever. And we haven't even used the whole data set. We've only used 80% of it. Like, to get a better result, I would go back and remove that validation set and just rerun the same steps and then submit that, because that lets us use 100% of the data. Where's our microphone?
I have 3 questions. The first one is like the class in this case is not balanced, unlike the dogs and cats.
It's not unbalanced. Like, it's not totally balanced, but it's not bad, right? It's like between 60 and 100. Like, it's not unbalanced enough that I would give it a second thought.
Okay, let's just say it's very unbalanced. Do you find it usually helpful to balance them? And it's
yeah, let's get to that later in this course, and don't let me forget, right? The short answer is that there was a paper came out about 2 or 3 weeks ago on this, and it said the best way to deal with very unbalanced data sets is to basically make copies of the rare cases.
My second question.
Yeah.
My second question is, I want to pin down the difference between pre-compute equals true and unfreeze. So you have these 2 options, right? So when you're beginning, after you added an augmentation, you said pre-compute equals true, but in that case, the layers are still free.
Right,
still frozen.
right. So it's, and not only they're frozen, they're pre-computed, so the data augmentation doesn't do anything at that point.
Right, but when you said pre-compute equals true.
Right.
But before you unfreeze everything, what does it exactly do? Like you only unfreeze the activation, is that?
So we're going to learn more about the details as we look into the math and stuff in coming lessons. But basically what happened was we started with a pre-trained network, right? Which was kind of finding activations that had these kind of rich features. And we were adding, then we add a couple of layers on the end of it, which start out random. And so with freeze equals, with everything frozen, and indeed with pre-compute equals true, all we're learning is those couple of layers that we've added. And so with pre-compute equals true, we actually pre-calculate like how much does this image have something that looks like this eyeball and looks like this face and so forth. And therefore data augmentation doesn't do anything with pre-compute equals true because we're actually showing exactly the same activations each time. We can then set pre-compute equals false, which means it's still only training those last 2 layers that we added, because it's still frozen, but data augmentation is now working because it's actually going through and recalculating all of the activations from scratch. And then finally, when we unfreeze, that's actually saying, okay, now you can go ahead and change all of these earlier convolutional filters.
So when you just do pre-compute equals false, you only unfreeze the last 2 layers.
So the only reason to have pre-compute equals true is it's just much faster. So it's like it's about 10 or more times faster. So particularly if you're working with like quite a large data set, it can save quite a bit of time. But it's never, there's no like accuracy reason ever to use pre-compute equals true. It's just a shortcut. It's also like quite handy if you're like throwing together a quick model. You know, it can take a few seconds to create it.
My last question, which I think you answered, is that so like in your suggestions to build a model, you have this staged approach. Like,
yeah.
What if like we just want like one initial setting without these like checking after each step, see where we're at? Do you recommend, like, for example, in the beginning we just do pre-compute equals false, and then we have these other learning rates, like the multi-cycle learning rate equation, and then we have unfreeze everything? Instead of,
I mean, if you wanted like if your question is like, is there some shorter version of this that's like a bit quicker and easier, I could like delete a few things here. Okay, I think this is a kind of a minimal version to get you a very good result, which is like, don't worry about pre-compute equals true, because that's just saving a little bit of time, you know. So I would still suggest use LR-find at the start to find a good learning rate. By default, everything is frozen from the start, so then you can just go ahead and run 2 or 3 epochs with cycle length equals 1, unfreeze, and then train the rest of the network with differential learning rates. So it's basically 3 steps: learning rate finder, train frozen network with cycle length equals 1, and then train unfrozen network with differential learning rates and cycle multi equals 2. So like that's something you could turn into, I guess, 5 or 6 lines of code total. I think it's a question behind you. Oh, and next door.
By reducing the batch size, does it only affect the speed of training?
Yeah, pretty much. So each batch, and again, we're going to see like all this stuff about pre-compute and batch sizes. We dig into the details of the algorithms. It's going to make a lot more sense intuitively. But basically, if you're showing it less images each time, then it's calculating the gradient with less images, which means it's less accurate, which means like knowing which direction to go and how far to go in that direction is less accurate. So as you make the batch size smaller, you're basically making it kind of more volatile. It's kind of like, it kind of impacts the optimal learning rate that you would need to use. But in practice, we're only, you know, I generally find I'm only dividing the batch size by like 2 or at most 4. It doesn't seem to change things very much.
Should I reduce the learning rate accordingly?
If you change the batch size by much, you can rerun the learning rate finder to see if it's changed it by much. But you know, since we're only generally looking at like a power of 10, it probably is not going to change things enough that you care. I think I'll pass it back there.
This is sort of a conceptual, sort of basic question. So going back to the previous slide where you showed.
Could you lift that up a bit higher?
Sorry, yeah, this is more of a conceptual, sort of basic question. Going back to your previous slide where you showed what the different layers were doing. Yeah, so on this slide, if I understand right, the meaning of, say, the 3rd column relative to the 4th column is that you're interpreting what the layer is doing based on what images actually trigger that layer to respond.
Yeah, so we're going to look at this in more detail. So these gray ones basically say this is kind of what the filter looks like. So on the first layer, you can say exactly what the filter looks like because the input to it are pixels, right? So you can absolutely say, and remember we looked at what a convolutional kernel was, like it was that 3 by 3 thing. So these look like they're 7 by 7 kernels, and you can say this is actually what it looks like. But later on, it's combining, you know, the input to it are themselves activations, which are combinations of activations, which are combinations of activations. So you can't draw it, but there's a clever technique that Zeiler and Fergus created, which allowed them to say, this is kind of what the filters tended to look like on average, right? So this is kind of what the filters look like. And then here is specific examples of patches of image which activated that filter highly. So yeah, the pictures are the ones that I kind of find more useful because it tells you this kernel is kind of a unicycle wheel finder.
Right, and so the pictures on the left, the schematics, they seem to match up pretty closely to what you're keying on the right.
Right.
How do we know that that's in fact what the filter is seeing?
We'll come back. Well, we may come back to that. If not in this part, in the next part. Probably in part 2, actually, because this paper uses, to create these things, this paper uses something called a deconvolution, which I'm pretty sure we won't do in this part, but we will do it in part 2. So if you're interested, check out the paper. It's in the notebook. There's a link to it, Zeiler and Fergus. It's a very clever technique and not terribly intuitive. Right. So, oh.
So you mentioned that it was good that the dog took up the full picture, and it would have been a problem if it was kind of like off in one of the corners and really tiny. What would you have done? What would your technique have been to try to make that work?
Something that we'll learn about in part 2, but basically there's a technique that allows you to kind of figure out roughly which parts of an image are most likely to have the interesting things in them, and then you can like crop out those bits. If you're interested in learning about it, we did cover it briefly in lesson 7 of part 1, but I'm going to actually do it properly in part 2 of this course, because I didn't really cover it thoroughly enough. Yeah. Maybe we'll find time to have a quick look at it, but we'll see. I know Yanette's written some of the code that we need already. So once I have something like this notebook that's basically working, I can immediately make it better by doing 2 things. Assuming that the size image I was using is smaller than the average size of the image that we've been given, I can increase the size. And as I showed before with the dog breeds, you can actually increase it during training. The other thing I can do is to use a better architecture. Now, an architecture, we're going to talk a lot in this course about architectures, but basically there are different ways of putting together like what size convolutional filters and how are they connected to each other and so forth. And different architectures have different like numbers of layers and sizes of kernels and number of filters and so forth. And so there are some, the one that we've been using, ResNet34, is a great starting point and often a good finishing point, because it's pretty, it doesn't have too many parameters. Often it works pretty well with small amounts of data, as we've seen, and so forth. But there's actually an architecture that I really like called not ResNet, but ResNext, which was actually the 2nd place winner in last year's ImageNet competition. Like ResNet, you can put a number after the ResNext to say like how big it is. And like my next step after ResNet34 is always ResNext50. Now you'll find ResNext50 can take like twice as long as ResNet34. It can take like 2 to 4 times as much memory as ResNet34. So what I wanted to do was I wanted to rerun that previous notebook with ResNext and increasing the image size to 299. So here I just said architecture equals ResNext50, size equals 299, and then I found that I had to take the batch size all the way back to 28 to get it to fit. My GPU is 11 gig. If you're using AWS or Crestle, I think they're like 12 gigs, so you might be able to make this a bit higher. But this is what I found I had to do. So then this is literally a copy of the previous notebook, so you can actually go File, make a copy, right? And then rerun it with these different parameters. And so I deleted some of the pros and some of the exploratory stuff to see, basically I said everything else is the same, all the same steps as before. There's in fact, you can kind of see what this minimum set of steps looks like. I didn't need to worry about learning rate finder, so I just left it as is. So transforms, data equals, learn equals, fit, precompute equals false, fit with cycle length equals 1, unfreeze, differential learning rates, fit some more. And you can see here I didn't do the cycle molt thing because I found like now that I'm using a bigger architecture, it's got more parameters, it was overfitting pretty quickly. So rather than like cycle length equals 1, never finding the right spot, it actually did find the right spot. And if I used longer cycle lengths, I found that my validation error was higher than my training error. It was overfitting. So check this out though, by using these, 3 steps, I got plus TTA, I got 99.75. So what does that mean? That means I have 1 incorrect dog, 4 incorrect cats. And when we look at the pictures of them, my incorrect dog has a cat in it. This one is not either. This one is not either. So I've actually got 1 mistake. And then my incorrect dog is teeth, right? So like we're at a point where we're now able to train a classifier that's so good that it has like basically 1 mistake, right? And so when people say like we have superhuman image performance now, this is kind of what they're talking about, right? So if you actually, when I looked at the dog breed one I did this morning, I was like, it was getting the dog breeds much better than I ever could. So like this is what we can get to if you use a really modern architecture like ResNext. And this only took, I don't know, like, I don't remember, it took like 20 minutes to train. So that's kind of where we're up to. So if you wanted to do satellite imagery instead, right, then it's the same thing. And in fact, the Planet satellite data set's already on Cresol. If you're using Cresol, you can jump straight there, right? And I just linked it into data/planet, and I can do exactly the same thing, right? I can image classifier from CSV, right? And you can see these 3 lines are actually exactly the same as my dog breed lines. How many lines are in the file, grab my validation indexes. This get data, as you can see, it's identical, except I've changed side on to top down. The satellite images are like top down, so I can flip them vertically and they still make sense, right? And so you can see here I'm doing this trick where I'm like do size equals 64 and train a little bit, first learning rate finder, right? And interestingly, in this case, you can see I want really high learning rates. I don't know what it is about this particular data set that this is true, but clearly I can use super high learning rates. So I used a learning rate of 0.2. And so I trained for a while, differential learning rates, right? And so remember I said like if the data set's very different to ImageNet, I probably want to train those middle layers a lot more. So I'm using divided by 3 rather than divided by 10, right? But other than that, here's the same thing, cycle mod equals 2, right? And then I was just kind of keeping an eye on it. So you can actually plot the loss if you go learn.shed.plot loss. And you can see here, here's the first cycle, here's the second cycle, here's the third cycle, right? So you can see it's like gets better, pops out, gets better, pops out, gets better, pops out. And each time it finds something better than the last time. Then set the size up to 128 and just repeat exactly the last few steps. And then set it up to 256 and repeat the last 2 steps. And then do TTA. And if you submit this, then this gets about 30th place in this competition. Right. So these basic steps work super well. This thing where I went all the way back to a size of 64, I wouldn't do that if I was doing like dogs and cats or dog breeds, because like this is so small that if the thing I was working on was very similar to ImageNet, I would kind of destroy those ImageNet weights. Like 64 by 64 is so small. But in this case, the satellite imagery data is so different to ImageNet. I really found that it worked pretty well to start right back at these tiny images. It really helped me to avoid overfitting. And interestingly, using this kind of approach, I actually found that even with using only 128 by 128, I was getting like much better cackle results than nearly everybody on the leaderboard. And when I say 30th place, this is a very recent competition, right? And so I find like in the last year, like a lot of people have got a lot better at computer vision. And so the people in the top 50 in this competition were generally ensembling dozens of models, lots of people on a team, lots of pre-processing specific satellite data and so forth. So like to be able to get 30th using this totally standard technique is pretty cool. All right. So now that we've got to this point, right, we've got through 2 lessons. If you're still here, then hopefully you're thinking, okay, this is actually pretty useful. I want to do more, in which case Crestle might not be where you want to stay. The issues with Crestle, I mean, it's pretty handy, it's pretty cheap, and something we haven't talked about much is Paperspace is another great choice, by the way. Paperspace is shortly going to be releasing Crestle-like instant Jupyter notebooks. Unfortunately, they're not ready quite yet, but they do have an ability to, basically they have the best price performance relationship right now, and you can SSH into them and use them. So they're also a great choice. And probably by the time this is a MOOC, we'll probably have a separate lesson showing you how to set up Paperspace, because they're likely to be a great option. But at some point, you're probably going to want to look at AWS. A couple of reasons why. The first is, as you all know by now, Amazon have been kind enough to donate about $200,000 worth of compute time to this course. So I want to say thank you very much to Amazon. We've all been given credits, everybody who's here. So thanks very much to AWS. So sorry if you're on the MOOC. We didn't get it for you, but everybody here is, it's like AWS credits for everybody. So, but you can get, even if you're not here in person, you can get AWS credits from lots of places. GitHub has a student pack, Google for GitHub student pack, that's like $150 worth of credits. AWS Educate, you can get credits. These are all for students. So there's lots of places you can get started on AWS. Pretty much everybody, a lot of the people that you might work with will be using AWS because it's like super flexible. Right now, AWS has the fastest available GPUs that you can get in the cloud. They're P3s. They're kind of expensive at $3 an hour, but if you've got like a model where you've done all the steps before and you're thinking this is looking pretty good, you know, for $6 you could get a P3 for 2 hours and run at turbo speed, right? We didn't start with AWS because, well, A, it's like twice as expensive as Crestle for the cheapest GPU, and B, it takes some setup, right? But I wanted to kind of go through and show you how to get your AWS set up. And so we're going to be going slightly over time to do that, but I want to show you very quickly, so feel free to go if you have to. But I want to show you very quickly how you can get your AWS set up, right, from scratch. So basically, you have to go to console.aws.amazon.com and it'll take you to the console, right? And so you can follow along on the video with this because I'm going to do it very quickly. From here, you have to go to EC2. This is where you set up your instances. And so from EC2, you need to do what's called launching an instance. So launching an instance means you're basically creating a computer, right? You're creating a computer on Amazon. So I say launch instance. And what we've done is we've created a fast AI, it's called an AMI. An AMI is like a template for how your computer is going to be created. So if you go to community AMIs and type in fast AI, you'll see that there's one there called fast AI part 1 version 2 for the P2. Okay, so I'm going to select that, and then we need to say what kind of computer do you want? And so I can say I want a GPU computer. And then I can say, I want a P2 X large. This is the cheapest, reasonably effective for deep learning instance type they have. And then I can say launch. And then I can say launch. And so at this point, they ask you to choose a key pair, right? Now, if you don't have the key pair, you have to create one, right? So to create a key pair, you need to open your terminal. If you don't have a terminal, if you've got a Mac or a Linux box, you've definitely got one. If you've got Windows, hopefully you've got Ubuntu. If you don't already have Ubuntu set up, you can go to the Windows Store and click on Ubuntu, right, and get it from the Windows Store. So from there, you basically go SSH-keygen, and that will create like a special password for your computer to be able to log into Amazon. And then you just hit enter 3 times, okay? And that's going to create for you your key that you can use to get into Amazon, right? So then what I do is I copy that key somewhere that I know where it is. So it'll be in the .ssh folder, and it's called idrsa.pub. And so I'm going to copy it to my hard drive. So if you're in a Mac or on Linux, it'll already be in an easy to find place. It'll be in your .ssh folder. Let's put that in documents. So from there, back in AWS, you have to tell it that you've created this key. So you can go to key pairs and you say import key pair, and you just browse to that file that you just created. There it is. I say import. Okay, so if you've ever used SSH before, you've already got the key pair. You don't have to do those steps. If you've used AWS before, you've already imported it. You don't have to do that step. Okay, but if you haven't done any of those things, you have to do both steps. So now I can go ahead and launch my instance. Community AMIs, search, FastAI, select, launch. And so now it asks me, where's your key pair? And I can choose that one that I just grabbed, okay? So this is going to go ahead and create a new computer for me to log into. And you can see here it says the following have been initiated. And so if I click on that, it'll show me this new computer that I've created, okay? So to be able to log into it, I need to know its IP address. So here it is, the IP address there. Okay, so I can copy that, and that's the IP address of my computer. So to get to this computer, I need to SSH to it. So SSHing to a computer means connecting to that computer so that it's like you're typing that computer. So I type SSH, and the username for this instance is always Ubuntu, right? And then I can paste in that IP address. And then there's one more thing I have to do, which is I have to connect up the Jupyter Notebook on that instance to the Jupyter Notebook on my machine. And so to do that, there's just a particular flag that I set. Okay, we can talk about it on the forums as to exactly what it does, but you just type -L 8888 localhost 8888. Okay, so like once you've done it once, you can like save that as an alias and type in the same thing every time. So we can check here, we can see it says that it's running, so we should be able to now hit enter. First time ever we connect to it, it just checks this is okay. I'll say yes. And then that goes ahead and SSHs in. So this AMI is all set up for you. All right, so you'll find that the very first time you log in, it takes a few extra seconds because it just kind of is getting everything set up. But once it's logged in, you'll see there that there's a directory called FastAI. And the FastAI directory contains our FastAI repo that contains all the notebooks, all the code, etc. So I can just go cd FastAI, right? First thing you do when you get in is to make sure it's updated. So you just go git pull, right? And that updates to make sure that your repo is the same as the most recent repo. And so as you can see, there we go. It's made sure it's got all the most recent code. The second thing you should do is type conda env update. You can just do this maybe once a month or so, and that makes sure that the library's there, all the most recent libraries. I'm not going to run that because it takes a couple of minutes, okay? And then the last step is to type Jupyter Notebook. Okay, so this is going to go ahead and launch the Jupyter Notebook server on this machine. Again, the first time I do it, the first time you do everything on AWS, it just takes like a minute or two. And then once you've done it in the future, it'll be just as fast as running it locally, basically. Okay, so you can see it's going ahead and firing up the notebook. And so what's going to happen is that because when we SSH'd into it, we said to like connect our notebook port to the remote notebook port, we're just going to be able to use this locally. So I see he says here, copy paste this URL. So I'm going to grab that URL and I'm going to paste it into my browser. And that's it, okay? So this notebook is now actually not running on my machine. it's actually running on AWS, okay, using the AWS GPU, which has got a lot of memory. It's not the fastest around, but it's not terrible. You can always fire up a P3 if you want something that's super fast. This is costing me 90 cents a minute. Okay, so when you're finished, please don't forget to shut it down. Right, so to shut it down, you can right click on it and say instant state stop. Okay, we've got $500 of credit, assuming that you put your code down in the spreadsheet. One thing I forgot to do, the first time I showed you this, by the way, I said make sure you choose a P2. The second time I went through, I didn't choose P2 by mistake. All right, so just don't forget to choose GPU Compute P2. Do you have a question?
No, you said 90 cents a minute.
Oh, 90 cents an hour. Thank you. 90 cents an hour. It also costs like, I don't know, $3 or $4 a month for the storage as well. Thanks for checking that. All right, see you next week. Sorry we went over. Oh, it normally takes a couple of days. Hi.
May I ask a question?
Yeah.
I fixed the learning rate, so it did much better.